In the beginning, there was nothing, no space and no time. Then there was light. Suddenly, a tiny speck of light appeared. It was infinitely hot, and inside this tiny fire was all of space. This was the beginning of time. The cosmic clock then began to tick. Time could now flow, and space could expand.
At the earliest moments of the Big Bang, if you take it back to t=0, everything in our universe, everything we can see, all the matter and all the energy in all of the galaxies was once contained in a region smaller than the size of a single atom today.
The idea that our universe was once tiny came from the brilliant work of American astronomer Edwin Hubble. Back in the 1920s, most astronomers believed that anything visible in the night sky was a star, and that all stars were part of our galaxy, the Milky Way. But Hubble wasn't convinced. He began to study a swirling cloud of lights called the Andromeda Nebula, and eventually showed that it was a star city, another galaxy far outside our own. He also showed that other galaxies were speeding away from ours, and the further away they were, the faster they seemed to be moving. The universe was therefore expanding. And if this were the case, then at some point in the past it must have been much smaller. And it must have had a beginning. The idea of the Big Bang was born. Theoretical physicist David Spergel is a Big Bang expert.
The Big Bang theory is not really a theory of how the universe began. It's really a theory of how the universe evolved.
No one knows exactly what happened during the Big Bang, but scientists do know that just a fraction of a second after the universe was born, this tiny super-hot fireball had already started to expand.
We don't know how the universe began. So we start our story when the universe was a billionth of a billionth of a billionth of a billionth of a minute old. Pretty young. The universe was the size of a marble.
Less than a trillionth of a second after the Big Bang, the marble-sized universe was very unstable and underwent an enormous growth spurt.
During this period of incredibly rapid expansion, space itself was expanding faster than the speed of light.
In the same way that this hot glass ball inflates, so did the baby universe, expanding in all directions at once. And as it expanded, it cooled. Immediately after the Big Bang, the universe was small enough to fit inside the palm of your hand. A tiny fraction of a second later, it was the size of Mars. Another fraction of a second, and it had grown to 80 times the size of the Earth. And our newborn universe continued to grow. But at this stage, it didn't contain matter. It was pure energy. Einstein's famous equation, E=mc², demonstrated that mass and energy are interchangeable. It provided us with the knowledge necessary to build nuclear weapons, and it also revealed how the universe created the first matter. When a nuclear bomb explodes, a tiny amount of matter is annihilated and converted into energy. In the baby universe, the exact opposite happened. It converted pure energy into particles of matter. But there was a problem. The universe created both matter and its arch-rival, antimatter. And when these two met, they obliterated each other. The infant universe was a war zone. If matter and antimatter had completely annihilated one another, the universe would have remained full of energy, with no galaxies, stars, planets, or life. But fortunately for us, there was an imbalance. For every 100 million antimatter particles formed, there were 100,000,001 particles of matter.
But there was that one extra particle of matter left over in each volume. And that was enough to account for everything we see in the universe today.
This tiny imbalance led to the formation of all the matter in the universe. Galaxies, stars, planets, even convertibles and ourselves.